next capacitor is connected with the parallel. The capacitor 2 microfarad is connected in parallel with the capacitor A. This one is only connected with the parallel with the, and this is a 2 microfarad capacitor connected with the parallel A. So the value of due to that case, the value of the capacitance is become Ca and 2 microfarad. These are in parallel, so we can write like that Ca plus 2. Now again, by comparing the charge, we can write like that 10 into, now 10 into Ca, but that one becomes this parallel, so we can write like that Ca plus 2 equals to 90 Cb, because the it rises to the 90 voltages for capacitor B whenever we are connecting the 2 microfarad capacitor is in parallel with the A. That's why we can write such that 10 equals to Ca plus 2 equals to 90 Cb. So 10 Ca plus 20 equals to 90 Cb. So we can write that Ca plus 2 equals to 9 Cb. Now this is equation of 2. So for comparing this equation 1 and equation 2, or put the value of equation 1 into equation 2, we can get that instead of Ca, putting the value of that one into equation 2, we can get that 2 by 3 Cb plus 2 equals to 9 Cb. So ultimately we get that 8.33 Cb equals to 2. So taking the Cb equals to 2 by 8.33, we get that 0.25 microfarad is a capacitance generated for capacitor B. And putting the value of Cb for equation 1, we get that Ca equals to 2 by 3 into 0.24 microfarad equals to 0.16 microfarad. So here just we get find out the value of capacitance A and capacitance B. The next question, derive the formula for the capacitance of parallel plate capacitor. Again, it is an important question and many times asked in a GTU exams. Find out the capacitance for the parallel plates. Some of the important parameter you have to just mention whenever we are talking about the parallel plates. The capacitors which are all connected to the same sources of the potential are said to be connected in parallel. Or you can say that all the capacitor get the same voltage, then it is known as a parallel. But if all the capacitor gets the different voltage, then these are connected in a series form. So here just taking one figure, that one C1, C2 and C3, three capacitors are connected in parallel form, and they are connected with the same supply voltage. So voltage is total voltage Vt equals to, write like that, V1 equals to V2 equals to V3. V1 is the voltage for the capacitor 1, V2 is the voltage for the capacitor 2 and V3 is the voltage for the capacitor 3. Ultimately what happens, the charges is different in a parallel capacitor and charges is same for the series capacitor. So here taking the individual charges for the capacitor 1, 2 and 3, we get that Qt total charge equals to Q1 plus Q2 plus Q3. This is the equivalent capacitance for the parallel plate. C capacitance equals to Q by V, or you can write like that Q equals to Cv. So using the equation of Q equals to Cv, Q equals to Q1 plus Q2 plus Q3 for the parallel circuit. Now putting the value of Q equals to Cv into the equation of Q equals to Q1 plus Q2 plus Q3, we get that Cv equals to C1V. Here the voltages are same, so we can write that Cv equals to C1V, Q1 equals to C1V, Q2 equals to C2V and Q3 equals to C3V. Now from the left side and from the right side, V is cancelled out, so ultimately we get that C equals to C1 plus C2 plus C3, and here your C is nothing but the equivalent capacitance. And generally with the general form, it is write like that Ce equals to sigma I tends to 1 to n times of capacitance connected with parallel Ci. Now one example based on the parallel plates, so we can easily identify how the value of the capacitor can be find out, how the voltages are the find outs. See that the 24 voltages are applied through the capacitor 1, 2 and 3. The value of capacitor C1 is 2 microfarad, C2 is a 4 microfarad and 6 microfarad. It means that 2 microfarad, 4 microfarad and 6 microfarad capacitors are connected in parallel with each other, and the EMF source given to them is 24 voltage. So we have to just find out the individual capacitance of a capacitor. Now applying the equation for the general form, CE equals to sigma I equals to 1 2 3 Ci. Here our n equals to 3, so sigma I equals to 1 2 3 Ci. And what is Ci? Ci is C1 plus C2 plus C3. So ultimately we get that CE equals to C1 plus C2 plus C3. So C1 equals to 2 microfarad, C2 equals to 4 microfarad and C3 equals to 6 microfarad. So taking the summation of all the three, we get that CE equals to 2 plus 4 plus 6, that is that 12 microfarad is the answer. So you can just find out for the n number of capacitor connecting in the parallel. Always mention that the equivalent capacitor is in parallel circuit, the equivalent capacitor should be always greater than the higher capacitance value. This is the hint for the parallel circuit, and obviously for the series circuit the equivalent capacitor is always less than the lowest capacitance value. These are the two notes when we are just proving the capacitor for the parallel circuit or for the series circuit. Now the voltage is the same, V1 equals to V2 equals to V3 equals to 24 voltage. So see, charges, find out that Q by V. So total Q equals to becomes C into V. Now C equals to 12 microfarad and V is 24 voltage. So total charge across the voltage capacitor, find out that Qt equals to 12 microfarad into 24 voltage equal to 288 microcoulomb. And the individual charge can be find out. Q1 equals to C1V, Q2 equals to C2V and Q3 equals to C3V. C1 equals to 2 microfarad, so Q1 becomes 2 microfarad into 24 voltage, that one is 48 microcoulomb. Q2 equals to C2V, V is the same, that is 24 voltage. C2 equals to 4 microfarad, so we get that Q2 equals to 4 into 24, that is 96 microcoulomb. And same as for the Q3, that one we get that 144 microcoulomb. So you can connect your capacitor in parallel form. You can easily find out the individual capacitance, individually charges generated through that capacitor, or you can just find out the equivalent capacitance. This is the individual capacitance for the, if you are connecting the capacitor 3 and the 6, or you can 2 and the 4 and the 2 and the 3. This is again one example. We just skip this example or just go through the quickly. This is the summary for the parallel plate capacitor. Equivalent capacitance is find out from the equation sigma I equals to 1 to n Ci. The charges are the summation for the parallel plate, like Q equals to Q1 plus Q2 plus Q3, but the voltages are same, like V equals to V1 plus V2 plus V3. But if you are taking the series circuit summary, then your CE becomes the 1 by Ci sigma I equals to n equals to into Ci, and your charge are not a summation, but the charge are same, Q equals to Q1 equals to Q2 equals to Q3, and your voltage becomes the V equals to V1 plus V2 plus V3. These are the reciprocal with each other. There is one video according to related to the parallel circuit.
Determine the charge, the voltage, and the equivalent capacitance for capacitors in parallel. Now this is the circuit we're going to use, and I'm going to go through all of this one step at a time, and these rules and these calculations all apply regardless of how many capacitors we have in parallel. Typically, it's shown as 3 capacitors, but whether we have 1, 2, 3, 4, 5, or many more, we apply the same rules and the calculations in the same way. And I'm going to go through and we're going to do 5 different things in this video. First of all, we're going to figure out, which is very obvious, or say what the total voltage gain is in this circuit. Then we're going to get the total or the equivalent capacitance. Okay, total equivalent, that's the same thing to me, the total capacitance of the circuit. And then we're going to get the total charge stored in the circuit. Those are our 3 totals: the total voltage, the total capacitance, and the total charge. And then after that, we're going to get the voltage drop or the change in potential, electric potential across each capacitor. And then we're going to get the charge that is stored on each capacitor. Okay, those are the 5 things we're going to do. We're going to do all that, and hopefully it'll be less than 10 minutes. Okay, the total voltage gain. That should be relatively straightforward. We have one battery over here. We have a 12-volt battery, and we just have the total voltage is 12 volts. Okay, so that's not that hard. Number 2, the total capacitance. What is the total or the equivalent capacitance? Same thing, equivalent total capacitance for this circuit. Well, we have 3 capacitors, 1, 2, and 3, a 12 farad, a 6, and a 5 farad capacitor, and they are hooked up in parallel. And it is very easy because the rule or the equation is the total capacitance, but once again, the equivalent capacitance is equal to the capacitance of the first one plus the capacitance of the second plus the capacitance of the third capacitor. All you do is add them up. So that's 12, 6, and 5 farads. Add them up and you get that the equivalent capacitance, the total capacitance, is 23 farads. Alright? Okay, next. What is the total amount of charge that is stored on this circuit? Now, we could go through and figure out the charge on this one, plus the charge on the second, plus the charge on the third, and then add them up and get the total. And we're actually going to do that later. But first of all, we can easily get the total charge by using our capacitor equation. Q equals C times V. And since we want to figure out the total charge, we have to use the total capacitance, or the equivalent capacitance, and the total voltage. Alright? And we can do it all in one step. And so that means that the total charge is equal to 23 farads, which we got over here, times 12 volts, which we got from our battery. Okay? Total capacitance, total voltage, multiply them together, you get 276 coulombs of charge. Alright? So that is how we did the first 3, the total voltage, the total capacitance, and the total charge. Those are our 3 totals. Now we can go through next and we can figure out what the potential difference is across each capacitor. Now this is also relatively easy because these are capacitors in parallel, and the rule is that the total voltage increase, or let's just say it this way, the potential difference.
Due to the shortage of the time, just skipping this video, but we just get the major or important information from that video, which we already talked that. You can just easily find out the total charge, total voltage gain, because voltage gain is the same whatever the battery supply you are connected with the main circuit. Now move towards the next question, that is question number 3b. There is one example. Then iron ring has a cross-sectional area 400 millimeters square and mean diameter of the 25 centimeter. So it is wound with the 500 tons, that is N. So if the value of the relative permeability is 250, to find out the total flux setup in the ring, the total coil resistance is 480 ohm and the supply voltage is 240 voltage. First of all, our target is to find out the given parameters or the datas. So first of all, that is A. There is a 400 millimeter square, the cross sectional area. The N is a turns, that is a 500 turns. Now R is the resistance, that is a 480 ohm. V is the supply voltage, that is a 250 voltage. Dm, that is a 25 centimeter. Relative permeability, that is a 250. That is a unitless. So now just by using that all the parameters just find out first of all the average length of the iron ring. Now the equation for the average length, L equals to pi into dm. The value of the pi is 3.14. You can put the value of pi is 3.14 into 25 dm, which is already given. So we get that L equals to 78.5 centimeter, and in the meter form it is 0.785. Now the current I equals to V by R. By using the Ohm's law, we can just find out the current passing through the device. That I equals to V is given is a 240 and R is a 480. So ultimately the 0.5 ampere current passing through the circuit. The next one, reluctance of the iron ring, that is a S. The equation for the reluctance for that iron ring is S equals to 1 by also L by mu 0 mu R into A. Mu 0 is the free space permeability, mu R is the relative permeability, and A is the area. So ultimately our S is L. The L is 0.785 by mu 0. The mu 0 is 4 pi into 10 raised to minus 7. This is the equation for mu 0. So now put the value of all this one, mu 0, we can get that 4 into pi 3.14 and 10 raised to minus 7 is a 250. 250 into 400 into 10 raised to minus 6. This is the area given to us. So ultimately our reluctance becomes 625 into 10 raised to 4 AT by Weber. Now the total MMF, that is magnetomotive force, the MMF equals to total flux into the reluctance. So that one is IN equals to flux phi into reluctance S. Now the current is 0.5 ampere and the turns are 500. So putting the value of I and N individually equals to 5 and S, that is a 625 into 10 raised to 4. So ultimately we can get the value of phi, that is 0.04 millimeter per meter into Weber. That is the flux generated in the circuit. Now the next question, the question number 5a, give the comparison between the series resonance and the parallel resonance circuit. These are the two forms of the resonance circuit, parallel and series. Just making the table and one by one parameter compare with the series and parallel resonance circuit. These are the topics of the parameters like the circuit types, how the circuit types behaves for the series and parallel, the power factor for the series parallel, impedance, current, frequency, magnification factor, quality factor, the nature and the applications. Starting with the circuit type. Circuit type for the series resonance is a purely resistive circuit. So the series resonance